x86-64 was changed to AMD 64. The success of the AMD 64 line of processors coupled with a lukewarm reception of the IA64 architecture forced Intel to release its own implementation of the AMD 64 instruction set. Intel had previously implemented support for AMD 64, 34, but opted not to enable it in hopes that AMD would not bring AMD 64 to market before Itanium's new IA64 instruction set was widely adopted. It branded its implementation of AMD 64 as M64T, and later rebranded it Intel 64. In its literature and product version names, Microsoft and Sun refer to AMD 64/Intel 64 collectively as X64 in the Windows and Solaris operating systems. Linux distributions refer to it either as X86-64, its variant X86_64, or AMD64. BSD systems use AMD64 while Mac OS uses X86_64. Long mode is mostly an extension of the 32-bit instruction set, but unlike the 16 to 32-bit transition, many instructions were dropped in the 64-bit mode. This does not affect actual binary backward compatibility, which would execute legacy code in other modes that retain support for those instructions, but it changes way assembler and compilers for new code have to work. This was the first time that a major extension of the x86 architecture was initiated and originated by a manufacturer other than Intel. It was also the first time that Intel accepted technology of this nature from an outside source. Extensions. Floating point unit. Early x86 processors could be extended with floating point hardware in the form of a series of floating point numerical coprocessors with names like 8087, 80287 and 80387, abbreviated x87. This was also known as the NPX, numeric processor extension, an apt name since the coprocessors, while used mainly for floating point calculations, also performed integer operations on both binary and decimal formats. With very few exceptions, the 80486 and subsequent x86 processors then integrated this x87 functionality on chip, which made the x87 instructions a de facto integral part of the x86 instruction set. Each x87 register, known as ST0 through ST7, is 80 bits wide and stores numbers in the IEEE floating point standard double extended precision format. These registers are organized as a stack with ST0 as the-top. This was done in order to conserve code space, and the registers are therefore randomly accessible only for either operand in a register-to-register instruction. ST0 must always be one of the two operands, either the source or the destination, regardless of whether the other operand is ST(x) or a memory operand. However, random access to the stack registers can be obtained through an instruction which exchanges any specified ST(x) with ST0. The operations include arithmetic and transcendental functions, including trigonometric and exponential functions, and instructions that load common constants, such as 0, 1, e, the base of the natural logarithm, log 2, 10, and log 10, 2, into one of the stack registers. While the integer ability is often overlooked, the x87 can operate on larger integers with a single instruction than the 8086, 80286, 80386, or any x86 CPU without two 64-bit extensions can, and repeated integer calculations even on small values, for example, 16-bit, can be accelerated by executing integer instructions on the x86 CPU and the x87 in parallel. The X86 CPU keeps running while the X87 coprocessor calculates, and the X87 sets a signal to the X86 when it is finished or interrupts the X86 if it needs attention because of an error. MMX. MMX is a SIMD instruction set designed by Intel and introduced in 1997 for the Pentium MMX microprocessor. The MMX instruction set was developed from a similar concept first used on the Intel i860. It is supported on most subsequent IA32 processors by Intel and other vendors. MMX is typically used for video processing, in multimedia applications. For instance, .mmx added 8 new registers to the architecture, known as mm0 through mm7, henceforth referred to as M. In reality, these new registers were just aliases for the existing X87 FPU stack registers. Hence anything that was done to the floating point stack would also affect the MMX registers. Unlike the FP stack, these MMN registers were fixed, not relative, and therefore they were randomly accessible. The instruction set did not adopt the stack-like semantics so that existing operating systems could still correct save and restore the register state when multitasking without modifications. Each of the MMN registers are 64-bit integers. However, one of the main concepts of the MMX instructions is the concept of packed data types, which means instead of using the whole register for a single 64-byte integer, quad word, one may use it to contain two 32-bit integers, double word, four 16-bit integers, word, or 8 8-bit integers, byte. Given that the MMX's 64-bit MMN registers are aliased to the FPU stack and each of the floating point registers are 80 bits wide, the upper 16 bits of the floating point registers are aliased in MMX. These bits are set to all ones by any MMX instruction, which correspond to the floating point representation of nans or infinities. (3D) Now. In 1997, AMD introduced 3D Now. The introduction of this technology coincided with the rise of 3D entertainment applications and was designed to improve the CPU's vector processing performance of graphic-intensive applications. 3D video game developers and 3D graphics hardware vendors used 3D Now to enhance their performance on AMD's K6 and Athlon series of processors. 3D Now was designed to be the natural evolution of MMX from integers to floating point. As such, it uses exactly the same register naming convention as MMX, that is mm0 through mm7. The only difference is that instead of packing integers into these registers, two single precision floating point numbers are packed into each register. The advantage of aliasing the FPU registers is that the same instruction and data structures used to save the state of the FPU registers can also be used to save 3D Now register states. Thus no special modifications are required to be made to operating systems which would otherwise not know about them. SSE and AVX. In 1999, Intel introduced the streaming SIMD extensions, SSE, instruction set, following in 2000 with SSE2. The first edition allowed offloading of basic floating point operations from the X87 stack, and the second made MMX almost obsolete and allowed the instructions to be realistically targeted by conventional compilers. Introduced in 2004 along with the Prescott revision of the Pentium 4 processor, SSE3 added specific memory and thread handling instructions to boost the performance of Intel's hyper-threading technology. AMD licensed the SSE3 instruction set and implemented most of the SSE3 instructions for its Revision E and later Athlon 64 processors. The Athlon 64 does not support hyperthreading and lacks those SSE3 instructions used only for hyperthreading. SSE discarded all legacy connections to the FPU stack. This also meant that this instruction set discarded all legacy connections to previous generations of SIMD instruction sets like MMX. But it freed their designers up, allowing them to use larger registers, not limited by the size of the FPU registers. Their designers created 8128-bit registers, named XMM0 through XMM7. Note, in AMD 64, the number of SSE XMM registers has been increased from 8 to 16. However, the downside was that operating systems had to have an awareness of this new set of instructions in order to be able to save their register states. So Intel created a slightly modified version of protected mode, called enhanced mode, which enables the usage of SSE instructions, whereas they stay disabled in regular protected mode. An OS that is aware of SSE will activate enhanced mode, whereas an unaware OS will only enter into traditional protected mode. SSE is a SIMD instruction set that works only on floating point values, like 3D now. However, unlike 3D now, it severs all legacy connection to the FPU stack. Because it has larger registers than 3D now, SSE can pack twice the number of single precision floats into its registers. The original SSE was limited to only single precision numbers, like 3D now. The SSE2 introduced the capability to pack double precision numbers too, which 3D now had no possibility of doing, since a double precision number is 64-bit in size. UHIC would be the full size of a single 3D now MMN register. At 128 bits, the SSE XMMN register Scout pack two double precision floats into one register. Thus SSE2 is much more suitable for scientific calculations than either SSE1 or 3D now, which were limited to only single precision. SSE3 does not introduce any additional registers. The advanced vector extensions, AVX, doubled the size of SSE registers to 256-bit YMM registers. It also introduced the VEX coding scheme to accommodate the larger registers, plus a few instructions to permute elements. AVX2 did not introduce extra registers, but was notable for the addition for masking gather and shuffle instructions.
Yes, that's a lot of information, but let's just continue. It's 6:20 p.m. A record 1 hour 34 minutes.
AVX 512 features yet another expansion to 32.512-bit ZMM registers and a new EVEX scheme. Unlike its predecessors featuring a monolithic extension, it is divided into many subsets that specific models of FPUs can choose to implement. Physical Address Extension, PAE. Physical Address Extension or PAE was first added in the Intel Pentium Pro, and later by AMD in the Athlon processors, 35, to allow up to 64 GB of RAM to be addressed. Without PAE, physical RAM in 32-bit protected mode is usually limited to 4 GB. PAE defines a different page table structure with wider pageable entries and a third level of page table, allowing additional bits of physical address. Although the initial implementations on 32-bit processors theoretically supported up to 64 GB of RAM, chipset and other platform limitations often restricted what could actually be used. X86-64 processors define page table structures that theoretically allow up to 52 bits of physical address, although again, chipset and other platform concerns, like the number of DIMM slots available, and the maximum RAM possible per DIMM, prevent such a large physical address space to be realized. On x86-64 processors, PAE mode must be active before the switch to long mode, and must remain active while long mode is active, so while in long mode there is no non-PAE mode. PAE mode does not affect the width of linear or virtual addresses. x86-64. In supercomputer clusters, as tracked by top 500 data and visualized on the diagram above, last updated 2013, the appearance of 64-byte extensions for the x86 architecture enabled 64-bit x86 processors by AMD and Intel, teal-hatched and blue-hatched, in the diagram respectively, to replace most RISC processor architectures previously used in such systems, including PowerISC, Spark, Alpha, and Athers, and 32-bit x86. Green on the diagram, even though Intel initially tried unsuccessfully to replace x86 with a new incompatible 64-bit architecture in the Itanium processor. The main x86 architecture, which is still used, as of 2014, in supercomputing clusters, is the PowerISA used by IBM Power microprocessors, blue with diamond tiling in the diagram, with SPAR Casa distant second. By the 2000s, 32-bit x86 processors' limits in memory addressing were an obstacle to their use in high-performance computing clusters and powerful desktop workstations. The aged 32-bit x86 was competing with much more advanced 64-bit RISC architectures which could address much more memory. Intel and the whole x86 ecosystem needed 64-bit memory addressing if x86 was to survive the 64-bit computing era, as workstation and desktop software applications were soon to start hitting the limits of 32-bit memory addressing. However, Intel felt that it was the right time to make a bold step and use the transition to 64-bit desktop computers for a transition away from the x86 architecture in general, an experiment which ultimately failed. In 2001, Intel attempted to introduce a non-x86 64-bit architecture named IA64 in its Itanium processor, initially aiming for the high-performance computing market, hoping that it would eventually replace the 32-bit x86.36. While IA64 was incompatible with x86, the Itanium processor did provide emulation abilities for translating x86 instructions into IA64, but this affected the performance of x86 programs so badly that it was rarely, if ever, actually useful to the users. Programmers should rewrite x86 programs for the IA64 architecture, or their performance on Itanium would be orders of magnitude worse than on a true x86 processor. The market rejected Itanium processors since it broke backward compatibility and preferred to continue using x86 chips, and very few programs were rewritten for IA64.
Yes, the video splits in 1 minute. I think I'll take a break because we have, I'm drinking cola, so I'm burping a bit. But we have the news, and then is in 5 minutes. The first evening news, and because it's Saturday we don't have the late evening news 9 p.m. and I make a video every day in Danish about the war in Ukraine. This is day 108, so I think I will start to upload this, but of course I not understand much of this. I don't understand, but I like to read it anyway, because then I better got understanding what X86 is. This is why I do this, because I like to learning, but I'm not computer programmer, and I'm not a computer scientist. Yes, I'll stop the video.